Welcome everybody to this presentation on warm starting quantum optimization. My name is Stefan Woerner from IBM Quantum. This presentation is based on a paper that my collaborators Daniel Egger, Jakub Marecek, and I recently put on the archive. And in the following, I'd like to provide you a little bit more details on these results. Combinatorial optimization has plenty of interesting applications, ranging from portfolio management, traffic routing to protein folding, but most of these problems are NP hard and thus very difficult to solve classically. Quantum computing is considered as a possible way to improve this, either by speeding up calculations or by providing better quality results. However, particularly for near-term quantum computers, the potential is still unclear. In this work, we introduce new variants of quantum optimization algorithms that improve upon the known techniques and open new avenues to the theoretical analysis of this potential advantage. Let's first look at the type of problems we are considering. So we mainly consider quadratic unconstrained binary optimization problems. So problems where we want to minimize a quadratic objective function over a set of binary variables. And you have a problem of that type illustrated at the right-hand side. To make this accessible to quantum computers, we usually map a QUBO to an Ising Hamiltonian and then to a ground state problem. To do this, we substitute the binary variables by spin variables, which take values plus minus 1 instead of 0, 1, and then these spin variables by Pauli Z matrices or tensor products thereof. And this gives us this Ising Hamiltonian, and then we are interested in finding the ground state of that. The ground state of this Hamiltonian directly corresponds to the optimal solution of the QUBO. And again, on the right-hand side, you see an example of the Hamiltonian resulting in this simple optimization problem. And as indicated in gray, the basis state 0, 0 would correspond to the ground state and also to the optimal solution of the QUBO. A common approach to approximate this ground state is the quantum approximate optimization algorithm, or QAOA. And here the idea is to, instead of searching over the full Hilbert space, over the full space of quantum states, to just search over a parameterized subspace. And this is achieved by constructing a parameterized quantum circuit that prepares states in this subspace and then minimize classically over these parameters. In QAOA, there's a special way to construct this circuit. This is first initialized by the equal superposition state, which we achieve by a layer of Hadamard gates. Then a parameterized evolution of this problem Hamiltonian, followed by a parameterized evolution of a mixing Hamiltonian, here denoted by HX. And HX is just the negative sum of the Pauli X matrices on the individual qubits. And here in the circuit diagram on the right, I highlighted the initial state and the mixing Hamiltonian, because that's what we'll change in the following. Now, since the equal superposition state that we use to initialize overlaps with all possible solutions, it also overlaps with the optimal solution. And in addition, it's the ground state of the mixing Hamiltonian. And thus, the adiabatic theorem implies that if we increase the number of times we repeat this evolution of the Ising Hamiltonian, evolution of the cost Hamiltonian, this is what we refer to as the depth of QAOA, then we converge to the optimal solution of the problem of interest, to the ground state. Now, we want to warm start QAOA, and thus we have to start with a problem that's easier to solve. And one way to achieve this is by just dropping these binary constraints of the variable. So instead of having variables take values 0 and 1, they can take arbitrary values between 0 and 1, or in general in the 0-1 hypercube. And if the matrix Q of this problem is positive semi-definite, then the resulting quadratic program is convex and can be solved efficiently classically. And you see this on the right-hand side. In general, since we are talking about binary optimization, we have that the variable x squared equals to x itself. And therefore, we can move the weights of the cost functions from the diagonal part of the matrix to the linear part and back. So we have some flexibility, and this always allows us to construct a convex quadratic program that we can solve efficiently classically that corresponds to our QUBO. Now, how can we use this to warm start QAOA? Let's suppose now we have the solution C star, which can take continuous values and is the optimal solution to the quadratic program resulting from our QUBO. Then we can use this to prepare initial state by replacing the Hadamard gates with single qubit Y rotations, as is illustrated here. And we'll choose the angle for these rotations such that every qubit is in a superposition between 0 and 1 that corresponds to the component of C star, as you see in this bottom formula. So our initial state now corresponds to the solution of the quadratic program that we can obtain classically. Second, we adjust the mixing Hamiltonian. And what you see here is the formula for the single qubit mixer. And again, this corresponds on the corresponding component of the solution to the continuous problem. And we choose this in such a way that the overall mixer, which is the sum of the individual ones, has the initial state that we prepared on the previous slide as its ground state. And its evolution can be implemented very easily just by applying 3 single qubit Pauli rotations on every qubit, as is illustrated here. All right, and this is what we call warm start QAOA. Let's now suppose we have such a solution C star that completely lies in the interior of the 0-1 hypercube. Then our initial state again overlaps with every possible basis state and therefore also with the optimal solution. It's again the ground state of our adjusted mixer, and therefore the adiabatic theorem implies that warm started QAOA converges to the optimal solution as we increase the depth. However, if there's a single component that takes the value exactly 0 or 1 in the continuous solution, then warm start QAOA will only be able to change the phase of the corresponding qubit and not really the value of this variable. So if that's not already the optimal choice, then we won't be able to converge to the optimal solution. To overcome this limitation, we apply a regularization. That's we introduce a small parameter epsilon, and we project the continuous solution C star into the epsilon to 1 minus epsilon hypercube instead of the 0-1 hypercube. And you see this illustrated on the right-hand side, where in blue you have the 0-1 hypercube, and in the dashed green you have the shrinked hypercube, and we project the solution into this smaller one. If we choose epsilon equals to 0.5, that would mean we always project into the middle of this cube, then we just recover the original QAOA. All right, let's now look how this works for an illustrative example, and this is portfolio optimization. So the goal here is to select a subset of assets from a given set of assets such that we maximize the expected return minus a weighted risk. And here we run numerical simulations and we choose a total of 6 assets, and we want to select 3 out of those. In the left plot, we looked at one random instance and we repeated the QAOA 10 times to find optimal parameters. And the x-axis shows the depth, which we increase from 1 to 5, and the y-axis, the corresponding energy. In orange, you see the standard QAOA and how the energy decreases. In green, you see the warm-started QAOA. And you see that the warm-started QAOA significantly outperforms the standard one, particularly at low depth. The blue line shows a warm-started initial state with the standard mixer, just out of curiosity, and we see that this does not work very well as expected. On the right-hand side plot, we test 250 random instances, now at depth 1. And the x-axis here is the approximation ratio. So if this is equal to 1, we found the optimal solution. And the y-axis is the number of counts, how often we find a certain approximation ratio. And note that the y-axis is in a logarithmic scale. What we can see here is that for about all the instances, the warm-started QAOA finds the optimal solution, while the standard QAOA only achieved an approximation ratio of about 75%. This was about continuous warm starting. Next, we want to look into how we can use rounded solutions to warm start QAOA. And here we focus particularly on the MAXCUT problem. So instead of a continuous quadratic programming relaxation, we now consider the Gurmans-Williamson STP relaxation with a randomized rounding. And how this works is it takes a particular graph, which is supposed to be here at the top right plot. This is transformed into an STP relaxation, a semi-definite program, that's then solved classically. And then from this solution, you can apply a randomized hyperplane rounding, which randomly generates cuts for this MAXCUT problem. And the nice thing is that Gurman-Williamson can be solved efficiently classically. And the theory implies that the generated random cuts satisfy that the expected value of these cuts is at least 0.878 times the value of the maximum cut. So it's a 0.878 approximation. And under the unique games conjecture, this is actually optimal. So there cannot be a better polynomial time approximation, a better classical polynomial time approximation. And what we now want to do is we want to use these Gurman-Williamson cuts to initialize warm start QAOA with regularization. And unfortunately, this does not seem to work very well. What you see in this plot on the right-hand side is simulations for 10 dense random graphs, each with 30 nodes, solved with 5 different Gurman-Williamson cuts at depth 1. In the x-axis is the regularization parameter epsilon that we change from 0 up to 0.5. And the y-axis is the resulting approximation ratio. And you see that you achieve the best results for a regularization parameter of epsilon equals 0. And since we start in a rounded solution, this means that the warm-started QAOA doesn't change anything. You just keep the cut. And that's not what we want. So question is, how can we change this? And for that, we adjust the mixer in our warm-started QAOA. And we just make a small adjustment. The top formula shows you what we had before. And then the bottom formula, you see that the minus sign in the angle went from the second RY rotation to the first one. And in the right-hand side, you see the corresponding results. And again, if we increase epsilon, you see that the performance goes down. But then at some point, it starts to increase again, peaking at 0.25. If you look at the top two small plots, those are zooms into the lower picture around 0 and 0.25, then you see that on average around 0.25, this really works better. So we get some improvement over the Gurman-Williamson cuts. However, now the initial state is not anymore the ground state of our mixer because we adjusted the mixer. That means we kind of sacrifice the convergence guarantee for the depth limit. So it still may converge, but we cannot argue anymore via the adiabatic theorem. However, it does perform much better. And so, of course, the question is why and what is special around epsilon equals 0.25. To answer that, we look into it in a bit more detail. So we assume a rounded solution X, which has values 0 or 1. And we set epsilon equals to 0.25. Now we set the gamma parameter equals to 0. That's the parameter that controls the evolution of the cost Hamiltonian. That means we do not apply this. And we set beta, that's the evolution of the mixing Hamiltonian, equal to pi over 2. This means that warm-started QAOA essentially only applies single qubit gates. And you see here the resulting gates for a single qubit. And in green, you see the result up to a phase. And you see if the rounded solution for a particular component equals to 1, then the corresponding qubit will be in state 0, while if the rounded solution is equal to 0, the corresponding qubit will end up in state 1. So we just invert the state that we started with. And this is quite nice because due to the symmetry of MAXCUT, where a solution X and a solution 1 minus X have the same value, we can recover the original cut. And therefore, with this particular parameters, we can also recover the original approximation ratio. But as we have seen in the simulation, we can also improve upon it. And in the following, we'd like to improve even a bit further. And for this, I want to introduce recursive QAOA. First, the standard version. Here we start with a problem, for example, MAXCUT. Then we run the QAOA, which gives us a quantum state. We evaluate the pairwise correlators between the variables for this quantum state, and we identify the pair of variables that have the strongest absolute correlation. And then we replace one of these two variables by the other one or minus the other one, depending on the sign of the correlation. That means we run one QAOA algorithm to eliminate one variable. And then we repeat with a smaller problem. And we do this until the resulting problem reaches a certain size. And once we reach this threshold, then we just continue by solving the resulting problem classically. Now, with warm start, we can do something similar. And particularly for MAXCUT now, we start by running the Gurman-Williamson algorithm on the initial graph. And this generates a couple of cuts. And for each cut, we run a warm started QAOA with a regularization. And instead of one quantum state, this now gives us a couple of quantum states. And we aggregate all of them to determine the correlations between the variables, the pairwise correlations. And then we follow the same logic. We identify the pair of variables with the strongest correlation and then replace one of them by the other or minus the other. And that way we can eliminate one variable, and we repeat this until we reach a problem of a certain size, and then we solve this classically. All right, and we tested this for different problem instances. So in the top row here, you see instances, the results for instances with 20 nodes. At the bottom, you see instances with 30 nodes. And the left column is 100 random graphs with an edge probability between a pair of nodes of 50% and random edge weights in plus minus 1. And the right-hand side column is again 100 random graphs, but this time dense random graphs with random edge weights in minus 10 to plus 10. And here we compare 4 different algorithms. The best cut out of Gurman-Williamson, out of 10 cuts, a standard recursive QAOA, the warm started recursive QAOA, and the recursive classical Gurman-Williamson, where you use the classical sampling to apply the same recursive scheme. And the plots again have on the x-axis the approximation ratio, where we separated the 100% in these gray boxes. That's the counts of the optimal solution. And the y-axis is again the counts. And what you can clearly see here for all cases is that the warm-started recursive QAOA really performs best. And the larger and the more difficult the instances get, so the most difficult one is the bottom right, the larger this difference gets. So this is quite nice. Now let's discuss the quantum advantage for combinatorial optimization from a bit more theoretical point of view. And again, here we talk about MAXCUT as an example, but this is similar for other problems. So we know that the Gurman-Williamson algorithm achieves an 88% approximation ratio. And we know that under the unique games conjecture, this is optimal. If we would only assume that P is not equal to NP, then the known upper bound on this approximation ratio would be 94%. And since the unique games conjecture is false for quantum computers, that implies that although we cannot expect that quantum computers can solve NP-hard problems in polynomial time, we may be able to get better polynomial time approximations. So in this right-hand side plot, you see the part that's accessible classically in green, the part that we don't think is accessible for neither for quantum nor classical in red. But then there's this orange part in the middle, which may be accessible classically, but for quantum computers, but not classically. And this is where we think warm starting is a very promising path to get there and to further analyze this. So to summarize, we introduced new variants of QAOA that improved the performance, particularly at lower depth over the known techniques, and they inherited the approximation ratios from classical algorithms. However, there are plenty of further directions to investigate, and here in this table you see the crucial questions to ask here. The first is what to round for warm starting. And we gave 2 examples, a quadratic programming relaxation and an SDP relaxation, but there are also other possible choices. The second is when to round. And you can do this either in the classical preprocessing, like we did in the Gurman-Williamson, or in the quantum circuit, like we did for the quadratic programming relaxation. And the last question is how to round. You can do this in the random hyperplane rounding or in the measurement in the quantum circuit. And the references that are indicated here can be found in the paper. So that's the end of my presentation, and I thank you very much for your attention.